Hi, my name is Alex Dalzell, and this is the recorded version of the talk for the FOCS conference titled A Distillation Teleportation Protocol for Fault-Tolerant QRAM. And it's based on joint work with a number of other folks listed here, many of whom are affiliated, like me, with the AWS Center for Quantum Computing, and some of whom have affiliations with other places as well. So the topic of this talk is quantum random access memory, or QRAM. And to motivate this question from a theoretical computer science perspective, I'd like to first talk about classical RAM. So the abstract picture of classical RAM is that it's a device or an operation which has stored within it a classical data set f of x with 2 to the n binary entries in kind of the most simple version, where if you give this device an address x specified by an n bit number, it will give you back the data element f of x stored at that address in the memory. So if you give it 101, for example, for this data table, it would give you back 1. Now, it's commonly assumed in the analysis of classical algorithms that RAM can be performed at cheap cost. So cost scaling polynomially at worst in the number of address bits n, which means polylogarithmically in the size of the data set f. And this assumption is sort of borne out in practice because we can construct semiconductor chips that implement this RAM operation for extremely large data sets with extremely low latency and energy costs and other sort of cost metrics that we might care about. So people have asked whether a similar assumption can hold for quantum random access memory. Where here we'll be studying the kind of most simple version of QRAM, where as with classical RAM, we're given a data set f of x, and we're given now, instead of a single address bit, we're given a superposition of the uh, n address bits. So we have a superposition over these 2 to the n possible address settings, and we wish to apply a phase -1 only on the computational basis states which have a 1 in this data set. So as a concrete example, if we're given this superposition of 4 entries of our data set with certain coefficients, we'd like to apply a -1 phase only on 3 of those 4 entries, and this should depend on the data set F. We can see that this is a unitary operation that we wish to apply, and we're going to call that unitary operation V of F. And then we can say that we would like to make an assumption, which we call the cheap QRAM assumption, that this unitary V of F can be implemented at computational cost that only scales polynomially in n, polylogarithmically in the size of the data. Now, is this justified? Well, this has been kind of the subject of significant controversy in the field of quantum algorithms. And it's an important controversy to get right because there have been a number of quantum algorithms that have been discovered that rely on this cheap QRAM assumption. So in the areas of quantum machine learning, where we're manipulating large vectors and matrices that are filled with entries that depend on large classical data sets. In the area of solving differential equations, where we might have some classical data set defining our design of the thing we're trying to model. And in the area of optimization, where we might solve linear programs or semi-definite programs which have classical data defining the instance. So many of these situations sort of begin with the assumption that QRAM has this cost and sort of say that's reasonable because RAM also has this cost. But we need to be a bit more careful about whether this is actually true. Now, how do we justify this cheap QRAM assumption? The starting point would be to look at this unitary V of F and write down a quantum circuit that implements this unitary. One such example is this one shown here, which has depth scaling only linearly in n, so logarithmically in the size of the data. Right? This is good news. This means that if we could implement this circuit in time scaling proportional to its depth, then we could have a latency for our QRAM operation that's logarithmic in the size of the data. However, this circuit, you'll see, has an exponential in n number of ancilla qubits. It also has an exponential number of gates. So If we were to try to implement this circuit at the logical level, right, because we know that these components, if implemented with actual hardware, will be noisy, we're going to have to, you know, replace each of these exponential number of ancilla qubits with a collection of physical qubits that encode a single logical qubit. We're also going to need to do syndrome extraction of our quantum error correcting code and classical decoding of the information that we're extracting. So if we think about this circuit on, megabytes or gigabytes of data, will be a huge circuit with tons and tons of physical qubits, generating tons and tons of syndrome data every second. And we're going to have to process this with simultaneous classical computation, which will look more like an HPC cluster than it will a single semiconductor compact classical RAM chip. Um, it's very questionable whether you can look at this and say that this should have only order n costs rather than order 2 to the n when you have all of these 2 to the n components that are very cost intensive. This objection is kind of made very clearly in this paper from 2023, for example. But it kind of reflects an older debate that's been going on for quite a while in the field of quantum algorithms. Um, so it really seems like this strategy of opening up this circuit, applying quantum error correction onto each component, is not really capable of justifying the cheap QRAM assumption in the fault-tolerant setting. Another strategy would be to not do that and just try to run this quantum circuit only at the physical level. So, in fact, there have been several works that have looked at constructing physical devices in photonic platforms and superconducting platforms and other physical platforms which can implement this unitary VFF or something similar to it directly at the physical level. This benefits from a certain property of noise resilience that this RAM operation possesses, has been shown to possess theoretically. But we won't expect that even with this noise resilience, we can achieve extremely low levels of error, right? So if we need to query our quantum RAM, you know, a billion times over the course of our quantum algorithm, then we need it to fail only once in a billion times, right? And we're not going to ever be able to achieve that in hardware. Um, so we know that we're going to have to apply some quantum error correction in some way or another. Now the question is there a way to do that without prying open the device, right? Can we apply quantum error correction outside the device rather than inside the device? And that is exactly what our protocol is going to achieve. So how does it work? Our protocol, first of all, is going to have a few components, right? We're going to have our physical specialized device that performs QRAM, shown in brown here. We're also going to have a normal fault-tolerant quantum processor that only has polynomial in n size and can perform fault-tolerant computation. Additionally, we'll have a classical computer which can talk to the quantum computer, receive measurement outcomes, and react adaptively to instruct the protocol on what to do next. The protocol will then consist of several steps, which we repeat iteratively. So there's going to be preparation of resource states, encoding of resource states, distillation of resource states, and then teleporting those resource states into the computation and performing a correction, which we do classically, and then iterating. So I'll explain all these things now. And it will be easiest to understand how it works by making an analogy with how we perform logical T gates in many schemes for fault-tolerant quantum computing. So one way of performing the T gate is to use resource states, also called magic states. So if you think of, you take some quantum error correcting code, you prepare the logical plus state, and you apply the logical T gate, you would get this encoded logical magic state shown here. This has been the subject of intensive study of how to do this with the lowest overhead possible. But needless to say, we have ways of preparing such states. Once you have such a state, you perform the logical T gate onto an arbitrary quantum state alpha by making an entangled measurement of this 2-qubit system to receive a single bit measurement outcome M, uniformly random, where if M equals 0, you've applied the T gate successfully onto the first register. And if the measurement outcome M is equal to 1, then you've applied a different gate onto the first register, and you require a corrective operation in order to apply in order to successfully apply the T gate. So in particular, it can be shown that the required correction is the phase gate, the S gate, which crucially is a Clifford gate. And so the full teleportation circuit with the correction looks like the one shown there. Our protocol is going to do something very similar, except for the QRAM unitary, which similar to the T state, the T gate is a diagonal unitary, except it's going to be on n qubits instead of only on 1 qubit. So in particular, we start with the all plus state, the equal superposition of all 2 to the n address settings. We apply the physical QRAM operation to get this unencoded resource state shown here. An equal superposition of all address settings with the -1 phase on those settings corresponding to a location in the memory where f of x equals 1. We prepare this state using our specialized QRAM device. Of course, it's noisy, so we only have a noisy version of this physical state. Now we send this physical state to our fault-tolerant quantum computer, and we encode it into a quantum error correcting code. Now the protocol doesn't really care what quantum error correcting code you want to use, but here, for the purpose of concreteness, I'm going to show what would happen for the surface code. So we take our n qubits from our resource state, we take n patches of our lattice, we send 1 qubit to each patch, we encode that qubit into a full encoded logical qubit, and now we have an n logical qubit state, which contains a noisy version of our encoded resource state. And then finally, once we have this encoded resource state, we apply a distillation procedure, which I'll explain later, to improve the fidelity of the state and make it closer to this encoded resource state we'd like to have. Now, how do errors work in this process, right? Of course, the physical device is noisy, so our initial physical resource states have errors. Additionally, the encoding step is not fault tolerant, and it can introduce additional errors into the logical state that results. But these are controlled and can be quantified in kind of a fairly strong way. So in the end, we can prepare these noisy encoded resource states without too much error, but we need the error to be much smaller, so we do this distillation process. But importantly, at this point, everything is encoded already, so the distillation process can be done fault-tolerantly using fault-tolerant set of universal gates. So no additional errors occur in that process, and in fact, it's designed to kind of correct the errors that have occurred in the previous processes. Okay, how do we use this resource state once we've prepared it? It's similar to the way we teleported in the T gate using a single qubit magic state. Here we have our n qubit magic state in the second n qubit register, and we have an arbitrary n qubit quantum state in the first register on which we would like to apply the logical QRAM unitary V of f. We apply this unitary by performing CNOT gates from the arbitrary state into this resource state and measuring the resource state in the computational basis, receiving measurement outcome m, which is uniformly random over all 2 to the n possible outcomes. If we were lucky and we got the all zero outcome, which occurs only 1 over 2 to the n of the time, then we will have applied the correct operation onto the first register and we can go home, right? We've applied the logical QRAM operation. But most of the time we get a different measurement outcome and we find that we applied the wrong operation onto the first register. We applied -1 to the f of x, XOR m, instead of -1 to the f of x. So similar to what happened with the T gate, we need to perform a correction operation. In particular, in order to undo this erroneous phase and then redo the phase -1 to the f of x that we wanted to apply, we need to send computational basis state x to itself with a certain phase shown here. And you can see that this is precisely a QRAM unitary V of f, but just for a different function f than we had before. So in particular, given an original function f, instead of applying V of f, we want to apply this new QRAM unitary for this new data set, where the new data set is computed from the old data set and the measurement outcome m. We call this the update rule, the way of updating the data set to give us the correction operation. And it's a very simple rule. It just pairs up these 2 to the n entries in the original data set and adds them together to define an entry of the new data set. On the one hand, it has a simple structure. On the other hand, we do have to touch every entry of the data set in order to implement this update rule. So in some sense, this classical update rule has complexity scaling exponentially in n. But this is just a classical cost. It's not a quantum cost. Nothing quantum is happening in this step. We just update the classical memory to contain this new data set. Then we can see what happens in our full protocol through this iterative process where here in this circuit, I've shown what we've explained so far, where we have an arbitrary state alpha, we have some classical data set F on 2 to the n, encoding 2 to the n data items. We prepare our physical state, we encode that state, we distill that state into a encoded high fidelity quantum RAM resource state. We teleport that resource state in and we receive a measurement outcome. And that measurement outcome requires us to do a correction, which we compute classically with our update rule. And then we perform the update in the exact same way that we performed the original QRAM operation using resource state preparation, teleportation, and again an update, right? Because of course we're going to need an update to the update, and we're going to need an update to the update to the update. It will keep going on for a while. And you might think that it will go on forever, that we'll just, unless we get lucky, we'll never terminate this process. But it can be shown that actually this will terminate after only n rounds. So if we keep updating this data set, regardless of what measurement outcomes we obtain, eventually, after n rounds, we will be guaranteed that our data set will be constant. So it'll either be the all zero data set or the all one data set. And that means that this unitary V of F that we need to do as a correction would just be proportional to the identity, and we can not do it at all. And that we can terminate the protocol and conclude that we've correctly applied the logical QRAM operation V of F onto our arbitrary state. This is the thing we wanted to do. We did that only using our specialized QRAM device, not needing to open that device and perform quantum error correction on it, only doing quantum error correction outside the device. So this constitutes kind of the main contribution of this work. Now, the only things I haven't really explained yet are how we do the encoding step and how we do the distillation step. And the encoding step I'll leave completely to the paper. We show how you can use results in the literature to perform this encoding to kind of quantifiable error for any quantum error correcting code you might wish. And for the distillation step, what I'll say about that is that the idea is we will leverage these results for quantum purity amplification, which solve the task of purifying many copies of an unknown quantum state. So why is that relevant for us? We can think of the physical device that prepares a physical resource state combined with the encoding step as preparing a mixed state that has the highest component of this mixed state is the state we want, but it has other states which are created by errors in those two processes. And so if we can just kind of distill away those errors, if we can purify this state, we will have obtained to high fidelity the state that we wanted to teleport into our computation. So we can study this as its own problem, where we want to take many copies of a mixed state and produce a single copy of its largest eigenstate. Now, this has been studied before, and we could use black box results from the literature on this, but we actually show a new method for this, which could be of independent interest, which leverages quantum principal component analysis to do density matrix exponentiation. The main idea, in just a very few words, is that you can, given an unknown state rho in, what you want to do is you want to prepare its largest eigenvector. So it would be nice if you could just do phase estimation on this input state using the basis of the state itself. This circuit shown here is the Kitaev's version of phase estimation, where if we could just use rho in as the Hamiltonian that we're trying to phase estimate, then we'd be able to extract with high fidelity this highest eigenstate, at least with some probability. Now, there's a lot of details to work out on how to do this. the main tool is quantum principal component analysis, which approximates this exponential of rho n using many copies of rho n. Um, and in the end, we're able to show that if the states rho n have like pure initial purity f, initial fidelity f with the state we want to create, then the total number of copies one needs is 1 over f squared times 1 over the target distillation error. This is a exponential improvement in f over kind of more simple methods like the iterated swap test. And it also matches the optimal complexity, at least in most parameter regimes, that was shown in 2024. But unlike this optimal method, our method is compatible with the streaming model where you receive copies of rho n one at a time and you don't have to process them all at once. So this, is a kind of new method for quantum purity amplification, which could have other applications. Okay, now I just want to conclude and reiterate that the main result here is a protocol that implements the logical QRAM operation in such a way where if your entire quantum algorithm needs to access QRAM only polynomial number of times, then it can do so using a polynomial number of accesses to this specialized device for performing physical QRAM and a polynomial number of fault-tolerant quantum gates. This physical QRAM device actually only needs to have fidelity that's very low. It can have very small signal with the state it's trying to prepare, as long as it's 1 over poly n. And overall, right, this kind of salvages potentially the ability to perform logical quantum algorithms that need QRAM in a realistic way. It also motivates that we might want to actually build these specialized QRAM devices, which have been the object of some study previously. But it's important to highlight the main overriding caveat of this entire result, which is that our protocol sort of essentially requires this classical update rule. And the classical update rule requires touching all 2 to the n entries of the classical dataset, and therefore, in a kind of purely gate complexity perspective, has complexity 2 to the n. So in some sense, what we've done then is compared to our method of writing it down a circuit and applying error correction on each component of that circuit, which had 2 to the n quantum complexity, we've reduced that quantum complexity to poly n complexity, but the cost has been an exponential amount of classical complexity. Now, trading quantum for classical complexity is often a good trade, but this is not quite fully satisfying for this reason, right? We would like to have a protocol which had both polynomial quantum and classical complexity. So this is a kind of a major open question for this line of research. As a final thought, I'll just mention that one direction we've thought about is whether this exponentially complex update rule could be parallelized and argued to have a much smaller complexity in like a parallel model, which is similar to how it works for RAM, right? RAM we know has exponential complexity in a gate model, but it's well justified to have lower complexity because it has parallel implementations in hardware. And we showed that indeed you can design a classical circuit that implements the update rule in only order n depth, but there are certain features of this circuit which are more complex than RAM. So in particular, it has like a dense wiring requirement that RAM does not have, which would also allow circuits like the one we write down to perform complex classical tasks like sparse matrix vector multiplication. So you can see the paper for a precise understanding of how this goes. And then the major open questions are kind of, besides trying to reduce the classical complexity, like if we have to deal with the classical complexity, are there applications where it's sort of okay to pay that amount of classical complexity? And also, are there ways to kind of perform a better version of distillation that could improve the overhead of this as a function of epsilon? Those are the 2 major open questions, and we hope that this kind of inspires a future avenue for research on quantum RAM moving forward. All right, thank you for listening and looking forward to seeing everyone at the conference.